Modern video diffusion models can generate impressive videos, but they still struggle with one major limitation: camera control. Imagine you want to generate a video where the camera slowly zooms out, pans to the side, or performs a cinematic movement like a dolly zoom. Traditional video diffusion models often cannot follow these instructions precisely. Some recent methods try to fix this by feeding explicit camera parameters into the model. But this creates a practical problem. Training data must include accurate camera poses for every frame. Those datasets are rare and usually contain mostly static scenes, which limits how well the models generalize. The key idea behind FloVD is surprisingly simple. Instead of representing motion using camera parameters, the authors represent motion using optical flow. Optical flow describes how every pixel moves between frames, or it creates a field of vectors in the image. It naturally captures both camera motion and object motion. And importantly, optical flow can be estimated directly from ordinary videos. That means the model can be trained on any video dataset without needing camera metadata. But FlowVD goes one step further. The system separates motion into two parts: camera motion and object motion. This separation is crucial because camera motion affects the entire scene while object motion only affects specific regions and pixels. To achieve this, FlowVD uses a two-stage generation pipeline. The first stage generates motion information in the form of optical flow. First, the model estimates the 3D structure of the input image using a depth estimation network. Using the depth map and the desired camera trajectory, the system simulates how pixels would move under that camera motion. This produces camera flow maps. Next, a separate diffusion model called the object motion synthesis model generates optical flow for moving objects in the scene. So it is defined in the motion of the image. So now we have two motion sources: background motion from the camera, foreground motion from objects. These two flows are then combined using a single unified motion representation, as you can see here. So in the second stage, the system actually generates the video frames. A diffusion model called flow condition video synthesis model takes two inputs: the original image and the generated optical flow maps. The flow maps act as a motion guide. During the diffusion process, the model receives multi-scale flow embeddings that tell it how each region of the image should move across time. As the diffusion model denoises the latent video representation, it uses this flow guidance to synthesize frames that follow the desired camera trajectory while maintaining realistic object motion. So the beauty of FlowVD lies in its representation. Optical flow naturally encodes pixel level motion, which implicitly captures the 3D relationships between the viewpoints. Because of this, the model can achieve precise camera control while still generating realistic object dynamics.